Okay, now in this part, we are going to study how to build a magnitude Bode plot for a complex transfer function for the function that we studied earlier, which has two poles and one zero. Okay, so the first thing that we will note, and we will look at the rules how to build the Bode plot, is that we have to start to sort the poles and the absolute value of zeros in order. So we notice here that we have pole 1 at 10 to the 4. We have pole 2 at 4 times 10 to the 4. And we have the 0, 1. It is found an absolute value at 10 to the 5. And this is in the frequency in radians per second. And we would like to build the magnitude of this transfer function in BDS, the asymptotic Bode plot for the magnitude in dB. So the first thing that we start with is that at S equal to 0, the low frequency gain for this function is equal to 1. This means that we are going to start from 0 dBs. Okay, now at each pole or a 0, we are going to have an inflection point or the slope will change. So every time we hit a pole, the slope, we add to the slope minus 20 dBs. Yani the old slope plus minus 20 dBs. And every time we hit a 0, we add to the slope plus 20 dBs. So we add to the slope plus 20 dBs. Therefore, in this graph here, when we hit the first pole, the slope was initially 0. So the new slope is going to be 0 plus minus 20. So the slope here will be minus 20 dBs per decade. And then when we hit pole number 2, the slope is going to be the old slope plus minus 20 dBs per decade. So this will be a slope of minus 40 dBs per decade. And then when we hit a 0, the slope is going to be the previous slope plus 20 dBs per decade. So this time it's going to be minus 40 plus 20. So it's going to come out to be minus 20 dBs per decade. Okay, so the slope is going to change based on whether I hit a pole or whether I hit a 0. The next thing that we need to determine in the Bode plot are the value of the gain at each one of these inflection points. So we have point number B and we have point number C. So we will learn how we determine the value at each one of these points. Before we determine that, we will follow the rules into how to build the Bode plot construction. The basic idea is that for the Bode plot, we are no longer using the exact function. We are building an asymptotic response, okay? And the basic idea is that this expression, the magnitude of A of S, which is equal to the square root of 1 plus omega over 10 to the 5 all squared over the square root of 1 plus omega over 10 to the 4 all squared times the square root of 1 plus omega over 4 times 10 to the 4 all squared. Okay, we are trying to find the asymptotic plot for the 20 log base 10 of A. Okay, and in a similar fashion to the way we build the transfer function for the pole and the individual pole, what we find is that when we hit a pole, we get minus 20 dBs per decade, and when we hit a zero, we get a plus 20 dBs per decade, because the zero appears in the numerator and the pole appears in the denominator. So the next sheet here will show us a rule, okay, how to build the Bode plot. So it tells us first, sort the poles and the zeros, and show their location on the omega axis. Of course, the zeros, we need to take the absolute value. And then we start with the dB value and the slope at low frequency. Yani if A of 0 equal A of n, then the starting dB value is 20 log of AN. I did the first step. And we'll talk about the starting slope in a second. So we will call this one A and B, but let us jump to 2. So after each pole we hit, is the slope after the pole is equal to the slope before the pole minus 20 dBs per decade. And anytime we encounter a zero, the slope after the zero is the slope before the zero plus 20 dBs per decade, just like what we explained before. Now, what they tell us here is that if my expression, for example, is 1 over s into 1 plus s over 10 to the 4, I have a pole at 0. Okay, so the starting slope is 20 dBs per decade times the power of the S term. Okay, يعني for this expression that we have here, we will rewrite this as S to the minus 1 times, let me write it clearly here, for this specific term that we have here, if my function is 1 over S into 1 plus s over 10 to the 4, I will write this as s to the minus 1 times 1 over 1 plus s over 10 to the 4. So for this expression, I have a pole at 10 to the 4, okay? The low frequency gain here, we cannot determine it because I have 1 over s. We'll take examples later how to determine it. But if we are asked about the starting slope is 20 dBs per decade times the power of the S term. So in this scenario, the power of the S term here is minus 1. So the starting is minus 1. So the starting slope is going to be 20 times minus 1. Okay, so the starting slope here is minus 20 dBs per decade. So this starts with a slope of minus 20 dBs per decade. Okay, and then due to the term s minus 1, and I hide it in yellow, it is due to the term s minus 1. Okay, and then when we hit the pole, the 10 to the 4, okay, then the slope will curve even lower, because it will be the slope after the pole will be the slope before the pole, which was minus 20, and minus 20 dBs per decade due to the pole. So this will be minus 40 here dBs per decade. Okay, so this minus 40 is because of the slope started at minus 20, and then we have here minus 20 due to hitting the pole. فإذا كان عندنا before this, in this example, we had a slope before the pole, which was minus 20, and then we hit the pole, okay, and we added minus 20 to it, so we ended up with minus 40. Okay, so let us take another example. Let us assume that we have a function which is 1 over s squared into 1 plus s over 10 to the 4. In this scenario, this is equal to s to the minus 2 over 1 plus s over 10 to the 4. Okay, so for this function, what we have is the pole is at 10 to the 4. The starting slope, we will not talk about the starting level because this is starting from a very high gain. The starting slope is, we'll take examples later, but what matters is to look at this here, is the 20 times the power of s. The power of s is minus 2. Okay, so the power of s here is minus 2. And basically, so this will be here in this region, we will start with a slope, and the slope value is nothing but 20 times minus 2, which is minus 40. يعني هيدي 20 ضرب الباور للأس اللي هي minus 2. Okay, so this is here, and now when we hit the pole, what happens is that the slope after the pole is equal to the slope before the pole, it became minus 40, and then we subtract minus 20, so then we will have a slope of minus 60 dBs per decade. Okay, so here we see that the slope now inherited from before the minus 40, and we added to it minus 20, so minus 60 dBs per decade. Okay, so this is the rules. These are the rules that we should care for. At this time, what matters most is sorting the poles and zeros, starting with the dB value, which is 20 log AM. And then when we hit a pole, we subtract minus 20 from the previous slope. When we hit a zero, we add 20 dBs per decade to the previous slope. Hello. These are the rules. Great. Hello. So we have here, this is the function. We hit the pole. We go down هيدي أول pole. We start with AM is 1. Okay, so 20 log AM is 0. So نحن بلشنا من 0 dB. Okay. We hit the first pole, then we have a second pole, then we have a 0. When we hit the first pole, the slope is minus 20 لأن هون ما في شيء slope 0. Then we hit the second pole, and when we hit the second pole, it will be minus 20 plus another minus 20, so it will be minus 40. And then we hit the third pole. هلا في شغلة كتير مهمة hit the third zero. في something that is important here is that, okay, we know that this is minus 20, we know that this slope is minus 40, but we need to determine the inflection point. Yani what is the value of the gain at the second pole? I know the starting gain, I know the slope, so I need to find what is the, and I know the 2 points, the 2 x points. Okay, and okay, if I know the 2 x points and I know one of the y points and I know the slope, I can find the other y point. The only catch is that this is log scale. يعني my x2 and x1 are nothing but log of omega 2 and log of omega 1. This is my x2, this is my x1. The slope is A, which is the slope, and the levels are gain 1 and gain 2. So أنا عندي ال x2s وعندي x1 بدي طلع y1 بدي طلع y2 knowing the slope. Okay, so let us see how we calculate the gain. Okay, so the way we calculate the gain is that we try to find the number of decades going from omega 1 to omega 2 يلي هو log 10 of omega 2 over omega 1. هيك نشوف. I'm going to bring up a slide so that we can explain this further. Okay, so here's what we discussed a little bit ago. We said in this graph, we know what is the value of gain 1, we know what is the value of x1 اللي هي بتساوي log omega 1, and we know what is the value of x2, which is log omega 2, and we know the slope, and we would like to find what is gain 2. So if we apply the traditional slope formula اللي هي y2 minus y1 over x2 minus x1 is equal to the slope, ساعتها we will know that this is gain 2 minus gain 1 over x2 اللي هي log omega 2 minus x1 اللي هي log omega 1 is equal to the slope. هلا نحن بنعرف إنه log A minus log B هي log of A over B. We just multiply this A times log of omega 2 على omega 1 plus gain 1 is equal to gain 2. Okay, so this is the formula. We can now, knowing omega 1 and knowing omega 2, we can calculate what is the gain at omega 2 or at the second pole. The general rule that we are teaching you here in this slide, the general rule that we are teaching you here in this slide is that what really log base 10 of omega 2 على omega 1 is, it is the number of decades. Okay, so multiplying them, for example, minus 20 dB per decade times the number of decades from omega 1 to omega 2, okay, plus the original gain will give me the new gain. It's the same formula, we're interpreting it in different ways, but this is very important because it will help you how to build your Bode plot and determine the different points on it. So knowing this, now we can continue constructing the Bode plot. We start from 0 dB here. Okay, the slope here is minus 20 dBs. We hit the second pole, the slope becomes minus 40, and then we hit the 0. The slope is going to be minus 40 plus 20, حيصير minus 20 dBs again. Now, at each one of these points, all the x values or the omega values are known to us. So we can calculate the gain, knowing the original gain and the slope of the interval. G2 is going to be equal to G1 اللي هي 0 dB plus the slope اللي هو minus 20 dB per decade times log base 10 of omega 2 اللي هي 4 ضرب 10 to the 4 على omega 1 اللي هي 10 to the 4. Okay, and if we know now G2, then I can determine the gain when I hit the 0. لأنه هيدا إذا سميناه G3 will be equal to G2 plus the slope between G2 and G3, which is equal to minus 40, okay, times log base 10 of هالمرة حناخد الأوميجا Z اللي هي 10 to the 5 over 4 ضرب 10 to the 4. Okay, if I know G2 and I know the slope, okay, and I know P2 and I know Z, I can solve for the value of G3. Okay, so فإذا هون in this last one we were using the information that we have here. We know this, and we know these 2 points, and we are trying to find this point, and this is the formula to find this point. Okay, so this explains how to construct the Bode plot and find the gain at the different levels. Therefore, we know the slope here, and we can calculate the dB value for this node. Okay, at these different points. On the Bode, there is a sheet that talks about the Bode plot phase construction. You can go over it, and we can set up a separate Q&A session for it. Okay, what really matters from the phase analysis is the following. What we care for the most is that, for example, in this expression where we have A of S equal 1 minus S على 10 to the 5 over 1 plus S over 10 to the 4 into 1 plus S over 4 times 10 to the 4, okay, is this is really, the expression is really 1 minus j omega over 10 to the 5, right? Over 1 plus j omega over 10 to the 4 into 1 plus j omega over 4 times 10 to the 4. هلا the contribution, the angle of A, it is equal to the angle of the numerator, يعني arctangent of B over A, الإيماجينري على الريل. The B هذا اللي بهمنا لأنه بالنيوميريتور بالزيرو we can have a minus sign. So the B is negative. So in this case, in the numerator, we will have minus, let me use the other color, minus B here minus omega على 10 to the 5, and the A is of course 1 here, okay? And this is from the numerator. And then the denominator, we will explicitly use minus arctangent of, طبعا هيدي B لها هي أوميجا على 10 to the 4 على 1, okay? وكمان الانجل, the second component of the denominator will be minus arctangent of omega over 4 ضرب 10 to the 4, okay? لأن الدينومينيتور نطلع الأنجل لفوق بصير بماينس، okay? Numerator, it happened in this scenario that it has an implicit minus in its complex term, okay? هلا, this means as omega tends to infinity, okay, each one of these terms is going to contribute by minus 90 degrees لأنه حيصير في عندي arctangent of minus infinity minus arctangent of infinity minus arctangent of infinity رح يطلع عنا minus 90 minus 90 minus 90 حيطلع عنا minus 270 degrees. فإذا the phase of this transfer function as omega tends to infinity is minus 270 degrees. Okay, this is one thing to note. We will practice with some exercises, but this is what we need to consider here. Okay, فإذا بالرول اللي حنشوفها على الموديل, it will tell us that a pole at infinity will contribute to minus 90 degrees. A zero at infinity إذا كان positive zero will contribute to plus 90 degrees. إذا كان negative zero مثل الexample اللي شفناه at infinity, it will contribute to minus 90 degrees. Okay, طيب, let us say that I have a system and that I am plotting my different poles and zeros. Okay, and I'm going to take them as multiples of 10 best to make it easy. So let us say that this is 10, this is 100, this is 1,000, and this is 10,000. Okay, and these are all radians per second. And let me assume that I have a pole, 0, and 0. And let us assume that all the zeros are positive. Okay, so then if somebody asks us what is the phase of this system at infinity, we should know that the pole contributes to minus 90 and that the positive zero contributes, pardon me, the positive zero contributes to plus 90 degrees. So هيدا عنده pole 0 0 يعني حيكون عنده 0 degrees is the phase at infinity. Okay, لأنه 2 ضرب minus 90 and 2 times plus 90. هلا let us assume that in this system that I have a system that has only 2 poles. So if we have a system that has only 2 poles, okay, and for example, we are looking for the phase at 10,000, okay, sorry, and we are looking for the phase at 10,000. What is the phase of the system at 10,000? Recall that when we studied the phase of the single pole أخذنا 3 نقط 0.1 omega 0, omega 0, and 10 omega 0. And we said that the angles will be this way. They will be 0, and then minus 45 at omega 0, and then we will have minus 90 at 10 times omega 0. So the minus 90 does not happen at infinity. In reality, we will gain minus 90 at 10 omega 0. So, and the phase is additive, as we saw. Each component or each pole will contribute to its own phase. So if we are looking to find the phase of A of S in this example that has 2 poles at 1000, okay, the first pole, by the time it reaches 100 would have contributed 90. من هون ورايح الفيرست بول أكيد هون بيكون عندي minus 90 due to P1, okay. لأنه 1000 على 10 أكبر من it's 100 times, and also P2 هون عندي 1000 على 100, so it is 10x, so كمان حكون حصلت على minus 90 degrees من P2 at this point. So any point beyond this, the phase will be minus 180 degrees. Okay, and in fact, the phase is additive. يعني نحن at any given frequency we are looking for, we can check each pole, what is its contribution, and then add the phases. But mainly نحن عادة we will ask you questions that are clear in the sense that, oh, for sure at 1000, pole 1 has contributed to 90 degrees and pole 2 has contributed to 90 degrees, and therefore the phase is minus 180 degrees. Or at infinity, a system with 2 poles is going to have minus 180 degrees as omega tends to infinity. Okay, a system with a 2-pole system, transfer function will have minus 180 degrees. Okay, so let us be comfortable with these concepts, and I will go over the slide that is on Bode in a separate session, or we can revise it later together. طيب, thank you. We'll catch up in class. Bye.